So how many of you remember factoring from Algebra 1? Was it your favorite thing to do in Algebra 1? No? You know, what do you need to know to be good at factoring? How about your multiplication tables? I mean, it all depends on you knowing those things pretty quickly, right? If I'm saying, like, what are the factors of 72 that add up to 17, you know, it can't be this long drawn out thing, you know, because we just assume you know that, like in half a second you can just spit it out. So what we do now is, this title is solving an equation by factoring, but before we can do that, we have to kind of go back over factoring and how do we factor, why do we factor. So we're going to do that. You know, if everything goes the way I think, we're going to take a quiz on 9:30. What is today? 9:22. So that's probably next Friday. Yeah. And it'll be mostly about factoring. All right. So we already know how to graph a quadratic function. That's what we did in the last couple of lessons. Okay. Now we learn how to solve the equations. And one method to solving is by factoring quadratic expressions that are set equal to 0. So before we can do that, we need to know how to factor. So that's kind of where we're going to go. Now, most of what I'm doing here, I'm kind of just using the book's order. And I don't necessarily agree with it 100%, but it gets all the information out. And if I don't use the book's order, then it's a little bit like, okay, we're going to do a little bit here, and then we'll jump ahead there, and then we'll jump back there. And to me, it just gets, you know, there's an expression being too cute by half. And I don't like to do that. So these are all the ways we learn to factor quadratic expressions. We're going to see 3 out of 5 of these today. And 1 out of 5 we won't see in the lesson, but you'll see it in the homework. And then the other one, the one we're leaving for next class, is this one that I'm calling not simple. Nobody else calls it that. That's just what I call it. Okay. I mean, just to give you a heads up on greatest common factor, okay? Something like this. 2x squared minus 4x. Whenever you look at any kind of an expression, the first thing you should be looking for is, are there any common factors in all the terms? Before you try to do anything else more fancy, just see if there's anything in common between the two terms. In this case, what is in common between the two? 2x. So you have to factor out 2x. And then what's left if I factored out a 2x? X minus 2. Okay, it's kind of a reverse distributive property. But you always have to be thinking about that. And that's what we call greatest common factor. And there isn't anything about it in the lesson today, but there's a homework problem or two where they've put it in even though they didn't cover it in the lesson. I guess they figure that's just the easy stuff. But here's the thing. We make so many mistakes on greatest common factor because we spend all of our time doing these trinomials. What's a trinomial? Tri for 3 terms, right? So that when you get something like this, and it only has 2 terms, you're kind of like, okay, now what do I do with it? Because I'm expecting 3 terms and it only has 2 terms. So at that point, it can only be 2 things. It can either be greatest common factor or it could be a difference of squares. And that's not a difference of squares. So it has to be greatest common factor. So what we start with in this class is the simple quadratic trinomial. So trinomial because it's 3 terms. What do you think a binomial is? 2 terms. Quadratic because it's got an x squared. And it's simple because a equals 1. Okay, we know the standard standard form of a quadratic expression, ax squared plus bx plus c. If you put 1 in the place of a, then you've got 1x squared plus bx plus c. And to factor that, you have to think of the factors of c whose sum is b. And that's where it comes into play. You got it in a multiplication table, right? Probably doing a quick sorting of what are all the factors of that last number and which ones would add up. Okay. Okay. So example, right? B is 5, C is 6. What are the factors of 6 that add up to 5? 3 and 2. Okay, now I'm going to show a little work on this off to the side. If you know your multiplication tables, this is a trivial exercise. But if you don't and you need help, like how do I reason my way through this when I'm really not that good at it? You know, what I would do is like take the 6 and put it off to the side and just say, what are the different pairings of numbers that multiply to give you 6? And understand that since the last number is positive, they're either both positive or they're both negative. Since the middle number is positive, they're both positive, right? So I can say it's either 1 times 6 or 2 times 3. So which of those two add up to positive 5? 2 and 3. Okay, so this is what the factoring looks like. X plus 2 times x plus 3. That's factoring. Right, it's two set of parentheses. What's inside each set of parentheses? A binomial linear factor. Linear because it's x to the first. Now, if you want to see where that comes from, then FOIL it. Right, we should be able to FOIL it and get back to where we started from. If I FOILed that, I would get x squared plus 3x plus 2x plus, I'll write 6. So then I'll write it like this, x squared plus 2 plus 3 times x plus 2 times 3. Right, so those two numbers multiplied to give us the 6 and they added to give us the 5. Okay, so try that one. Okay, so what was the right factoring? Does it matter if you say that reverse the order? Commutative property says it doesn't matter. Okay, now I'm going to show you something here. If you're one of those that struggles with factoring sometimes because you don't really know your multiplication tables that well, here's how you can do this with the calculator. Okay, in your calculator, go to y equals and put in 20 divided by x. Okay, enter. And then go to the table of values. Does it look right? Oh yeah, I'm scrolled down a little bit. Okay, the X button is right here. Okay, this is important because if you didn't know, how would you know? Okay, but we don't want to get too far into this class and still be trying to do alpha X down here because you have a button for X. It's right there. Yeah, you really should. Okay, now you know. Okay, so now look at this table, go to the table of values, right? Go to y equals and put in 20 over x, and then go to the table of values, second graph, and you're going to see something like this. And now here's all the factors of 20. 1 times 20, 2 times 10, 4 times 5, okay? Now, as soon as the numbers in the left column get bigger than the ones in the right, you're done. There's no more. It's just going to repeat the same factors in reverse order. Okay, so you have trouble, like, you know, what are all the factors of 72? 1, 2, 3, 4, 6, 8, 9, you know, it goes on and on and on. There's a lot of factors. But this will give you all right in front of you. So then I would go like this. Okay, it's going to be 20. So we said it's 1 times 20, 2 times 10, or 4 times 5. Now, if the last number is positive 20, but the middle number is negative 9, what do you know about your two numbers you're looking for? They're both negative, right? So I should put negatives in front of all of these. Negative, 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 negative. And then figure out which of these add up to negative 9. And the answer is these. That's why we use x minus 4 times x minus 5. Okay. Okay, try that one. So then 18 could be 1 times 18, 2 times 9, 3 times 6. Since it's a negative 18, that means one of those numbers has to be negative. Which is going to be the negative, the bigger number or the smaller number? The bigger number has to be the negative. So which one of those adds up to negative 3? That one. X minus 6 times x plus 3. That was terrible. Done. See if I got another in there. Try this one. What do you notice? Are there any factors of 9 that add up to negative 3? So it's not factorable. That can happen sometimes. You're going to get something that's not factorable. You know, if you go back to the original slide, the bullets, it says, students should know how to use an appropriate method to solve. Okay, well, in this kind of problem, factoring is not an appropriate method because it's not factorable. So that makes you go on to another method. Okay, so there's nothing wrong with that. It just means go to emergency backup plan B. Okay, so this is not factorable. Okay, try that one. I'll give you 10 seconds. Okay. Factors of 63. 7 times 9. I mean, to me, that's like one of those common factors that we all kind of should remember. Like 79 is 63 is 7 times 9. How about 56? How about 54? 69. Yeah, I mean, those are kind of, they just jump into your head right away. And you look at it and say, 9 and 7, if they happen to be opposite signs, sure enough, I can add up to that positive 3, so positive 2. So, you know, 63, there's not many different. 1 times 63, 3 times 21, and then it's 7 times 9. Right? And then if the bigger one has to be positive, so that's it right there. R minus 7 times R plus 9. Piece of cake. Okay, so here's two other kinds of factoring. You should have copied this block, you know, in the extra credit homework. One is called difference of squares. And the other one is called perfect square trinomial. So notice why they're called that, right? a difference of squares mean it's a difference. What does difference mean in math? It's a subtraction, right? So it's got to be a subtraction. If you saw x squared plus 4, that's not a difference of squares. This wouldn't work because it's a plus. And then it has to be two quantities that are being squared. Like in this case here, x squared minus 4, it's actually x squared minus 2 squared. So there's x is being squared and 2 is being squared. So according to the formula, it should be a squared minus b squared is a plus b times a minus b. X squared minus 4 is x plus 2 times x minus 2. Okay? Now, it gets a little more complicated than that when a does not equal 1, but we're not doing that today. Okay? At this point, they're all going to be just 1x squared. So you just have to think of what's the square root of whatever's on that sign. Now, notice the perfect square trinomial. Ultimately, it factors as one factor squared. So that's why it's called a perfect square trinomial. X squared plus 6x plus 9. I mean, we could factor that with just what we learned about simple quadratic trinomial. What are the factors of 9 that add up to 6? 3 and 3. So it's x plus 3 times x plus 3. Since these are the same, you are actually squaring x plus 3. That's why it's called perfect square trinomial right there. Because ultimately it will factor as one factor squared. And again, when you've got a 1 in front right here, honestly, I doubt that you're using a formula like this. You're probably just doing the what are the factors of C that add up to B. And that's fine. I don't find this one to be so useful, but a little bit. So you should have already copied that. That came right out of the block. So let's do these together, and then I'll do the U-tries for you. So the first one, again, what is that pattern called again? X squared minus 49? Difference of squares, right? And so it's literally x squared minus 7 squared. And according to the formula, how should that factor? X minus 7, x plus 7. Okay, so the next one, again, if I just use simple quadratic trinomial reasoning, what are the factors of 36 that add up to 12? 6 and 6. So this is going to be x plus 6 times x plus 6, which is x plus 6 squared. Again, and notice, because we make a lot of mistakes with this in this class and higher up too, that x plus 6, Joby. Yeah, it's supposed to be d. I'll go back to that. Notice that x plus 6 squared, it's not x squared plus 36. Right? There's a middle term there. So don't ever try to just distribute this 2 inside. That's a very common mistake we make. So don't try to do that. And yes, it should be d. Get a smaller one like that. So that is d and d and d. Okay, and so this last one is, should be z minus 13 squared. So the square root of 169 is 13. Okay, so try those two. I'm going to keep the recording rolling because I don't think this should take you long. So is this right? What's wrong with that? It should be 3 and negative 3. I see that mistake a lot. Okay? Remember, it's the square root of 9. And you could always, figure that out for yourself. You could FOIL it and see if you got the right thing. Another way you can think, if you have trouble with difference of squares, just trying to give you another option. Let's say you're okay with that simple quadratic trinomial so far. Then just think of this difference of squares like x squared plus 0x minus 9. So now you're looking for the factors of negative 9 that add up to 0. 3 and negative 3, x plus 3, x minus 3. Okay, what'd you say on the last one? Yep, in one order or the other. Doesn't matter. Okay, then try this one. Your first clue is you see the C is a perfect square. And you just see if the middle term adds up. If it does, you're good to go. What kind of factoring pattern is this? Perfect square trinomial, right? So what'd you say in the first one? This should be y plus 8 squared. How about the last one? W minus 9 squared. So why plus on the first one and minus on the other one? Yeah, because that's a plus, that's a plus. Since that's a minus, that's a minus. What do you mean? No. Okay, so now we know how to factor a little bit, right? We've learned a few of these. Some of this is probably not new. You've seen this a little bit before. Now we can use factoring to solve when you've got a standard form quadratic expression set equal to 0, then you can use it to solve. And this one I made a mistake on. I meant to fix these before now, but I didn't. That should be a minus. Okay, so now if I have to solve that equation, somebody just says solve that equation, and I didn't know anything else, I'd say, well, what does solving usually mean? It means isolating the x on one side, the answer will be on the other. And you can do that in Algebra 1 when all you deal with are linear equations, then you can always isolate the variable. But in a problem like this, the variable is in 2 different terms, and they're not like terms. So I can't combine them into one term. So there's no way to isolate the variables. That's where factoring comes in. So let's write this, instead of being in standard form, let's write it in a factored form. And let's see, what are the factors of negative 15 that add up to the negative 2? Well, one's positive and one's negative, right? X minus 5 times x plus 3 equals 0. Okay, so now at this point, we have factored form equals 0, and we can use this 0 product property. Remember that there is a 0 property of multiplication, which says that 0 times anything is 0. Okay, but there's a corollary to that too. Is there's no other way to make a 0 with multiplication other than you multiply by 0. You can't find any 2 other numbers that multiply together to give you a 0. That tells us that one of our factors must be 0. It's the only thing that could happen. So we can make the 2 equations out of that. One of them will be that x minus 5 equals 0. And the other will be that x plus 3 equals 0. And now both of those are linear because it's x to the first. There's an x in only one term, so you can easily isolate it to solve. So add 5, subtract 3. So the solutions are 5 and 3. Now again, think of it I mean, I would tell you that you probably won't be writing these steps down very often, because when you see that there, it probably will become just obvious. What number would I plug in here to make this factor equal 0? 5 minus 5 is 0, right? So if it says minus 5 there, the solution is actually plus 5. Okay. Same thing here. What would I plug in for x here to make this equal 0? Negative 3. So when this is a plus, then actually the solution is a minus. So they kind of have an opposite sense like that. And actually most of the time we're kind of doing that in reverse. If the solution is 5, it must have come from a linear factor of x minus 5, right? If the solution is negative 3, it should be x minus negative 3, which is x plus 3. Okay, let me try another one here. So here's the important thing. When we said that right up at front, we said this is for how you solve a quadratic trinomial or quadratic expression that is set equal to 0. So if it's not set equal to 0, like this one right here, it's actually equals 4, you're going to have to like get the 4 over onto the other side so that it is equal to 0. Then you can use any of our methods, but you can't do this until you start with get everything on one side, 0 on the other. And it should be in standard form: the squared term, the linear term, the constant term. And you know, that doesn't work. We don't have any other properties like that. I've seen kids that had like a quad, maybe it said x squared minus 4x minus 4 equals 5. And so they set each factor equal to 5. We don't have a 5 product property. We have a 0 product property, right? So it only works for 0. Yeah. No, it might just say factor. Yeah. No, that's the part you've got to figure out. Okay. Okay, so solve by factoring. Again, it's not set equal to 0, so let me subtract 36 from both sides. Right, if it was a positive on the right, it's a negative on the left. And then now let's factor it. Right, 36 could be 1 times 36, 2 times 18, 3 times 12, and 6 times 6. Since the middle number is negative, it must be that the bigger of the two is negative. Okay, so, oh, I forgot, didn't I? 4 and 9. I forgot the one that was going to work. So it must be that. So we're going to say x plus 4 times x minus 9. So what are the solutions? Yeah. So x equals negative 4 and 9. You don't, for a simple linear factor like that, just 1x plus or minus a number, you can just go right to your answers. So you try to do that one. And let me just say that if you get a problem like this where, you know, the easiest thing to do might seem to be to move the x squared over, but then it becomes a negative x squared. And you try to keep x squared positive, i.e. move the x in the 42. So you subtracted the x and the 42 to the other side. That left is 0. And then you factored. So there's two kind of common errors that I see. One is you'll get a problem that says solve by factoring, and you'll factor, and then you'll stop, but you didn't actually solve the equation, right? Remember that if it says to solve, that means you've got an equation, and you've got to end up saying, like, answers. The other problem I'll see sometimes is that actually you get a problem that just says factor, and you automatically set it equal to 0 and give answers. But that wasn't the problem. It's like you're just automatically doing something, which I mark off for, because too much of the time I think you don't know what's actually being asked, so you just throw everything at the wall and hope you'll get credit for it. But you need to just answer the question in front of you. Don't make it into something else. Yeah. What do you mean? Here? What would you plug in here so that this expression equals 0, right? 7 minus 7. Yep. Okay. You know, when I first made up these slides, I kind of went a little bit different way, and then I kind of realized what the book was doing with this. It is true, you can solve an equation by graphing, and that helps us to understand why you can do what we're about to do by factoring. But ultimately, we will solve by graphing, but we're really not doing that now. We'll use the calculator just to show why it works. But let's say you're given an equation to solve, okay? And it could be an equation that's not set equal to 0 already. You make it set equal to 0, so you have something like that. And then, as a method to solve, you say, I'm going to turn this into the function by making y equals that expression. Okay, that's not what you were given, right? This is a one variable equation that you want to solve for x. This is a function that has a graph. If you want to find the solutions to this on that graph, then you need to find where does y equal 0. On the graph, where does y equal 0? On the x-axis. So what are you looking for on the graph? You're looking for the x-intercepts. Right? So if you graph this, right, you're going to get something that looks like that. Now, we already been doing on the y-axis x equals 0. Well, on the x-axis, y equals 0. So if we go to the y-axis, then we're at exactly that point where this function becomes this equation. So you just have to find these 2 points. Find the x-intercepts, and you're done. Now, we can do it with this one if you want to just see how that works. Go to your calculator and put in here x squared minus x minus 12. Okay, you know where you're going for that? You go to the y equals. Right, go to y equals and put in that. Okay, then how is it that you look at the graph? You hit graph button right there. So hit the graph button, and you should see a parabola, because we know that's what the shape of a quadratic is, and you should see pretty easily what those 2 x-intercepts are. And what are they? It looks like -3 and +4. Okay, now, you could confirm that by going to the table of values. Where do you find the table of values? Second graph, right? Yes. So look at -3. I scrolled up so I could see x equals -3 and y equals 0. Okay, that's what we expected. And now scroll down to 4. And there, sure enough, when x equals 4, y equals 0. So where does y equal 0? The x-axis. Okay, so the x-intercepts of the graph of the parabola are also called the zeros of the function. The zeros are the values of x that make the function equal 0. but they also happen to be the solutions to the quadratic equation. And sometimes the solutions to the quadratic equation are called roots. So actually all four of those terms are kind of referring to the same thing, even though they're not exactly saying the same thing. But they're used so interchangeably that I think sometimes even good math people that know better are using kind of the wrong term, like finding the roots of a function. Okay, function doesn't have roots, or finding the zeros of an equation. Equation doesn't have zeros. But it's okay. I mean, you should just understand x-intercepts equals zeros equals solutions equals roots. It's all pretty much the same thing. So good with that? We're almost done. Okay. So in fact, we're not going to be saying now solve by graphing, because I can't send a calculator home with you. All of these that we're looking at right now are actually factorable. So instead, it's going to be saying find the zeros, and that's why this should have said a y. Find the zeros by factoring. Now we know that the zeros are just going to be the solutions to that equation, x squared plus 5x minus 14. Okay, so we're going to do that by factoring. What are the factors of negative 14 that add up to positive 5? Positive 7, negative 2. And so what are the solutions to that? Negative 7, positive 2. Okay, find the zeros by factoring. Okay, and again, I'm going to change, that was sloppy of me, y equals. Find the zeros of this function. Okay, we know that that's like solving this equation. And I think we actually factored this one already, didn't we? It was x plus 6 squared. So what is the only zero for this function? Negative 6. So again, somebody brought this up, already said on the side, right? That means that this thing only touches the x-axis in one spot, so it must just have its vertex right on the x-axis at negative 6. I mean, otherwise, it's going to have two zeros, right? It goes down and then up again. But if it only has one factor, then it's only got 1 0. It means it touches in one place and goes back to the same side. So you try that one. Find the zeros by factoring the equation, or by solving the equation by factoring. There are the zeros. 10 and negative 3, right? So you say, I have to solve this equation, and the factors of negative 30 that add up to negative 7 are negative 10 times 3. So it's x minus 10, x plus 3. So x equals 10, and x equals negative 3. Okay. Last one. Find the zeros by factoring. How did it factor? So what is the only zero? And again, what does that tell you about the graph of the function? The vertex is right on the x-axis, right? Okay. So let's see. This comes from the SOLs. Factor polynomials, quadratics are polynomials, by applying general patterns including difference of squares, sum and difference of cubes, that'll be next chapter, and perfect square trinomials. Factor completely over the integers, we're about 2/3 the way there in terms of how many things to learn. And then solve a quadratic equation over the set of complex numbers using an appropriate strategy. So sometimes it won't tell you how, it just says solve, and you've got to figure out what to do with it. The homework is